Welcome to AI Paper Podcasts. Today we are breaking down From Kepler to Newton, Inductive Biases Guide Learned World Models and Transformers by Zheming Liu and others at Stanford. So here's the core problem they're tackling. Previous research from Vafa et al. Showed that transformers trained on tons of planetary motion data like 20 billion tokens don't actually learn physics.
Not at all.
They don't get Newton's laws. They just become really good statistical curve fitters. They're memorizing shapes, not understanding forces.
Exactly. And this paper offers a fix with three really specific inductive biases. First is spatial smoothness, basically, fixing how we tokenize continuous data so we don't break space itself.
Right.
Second is spatial stability. They use regression, but with something called noisy context learning to stop errors from piling up. And the third, this is the big one, is temporal locality. By restricting the model's memory to just the last two frames, they force it to stop fitting geometric curves, the Keplerian way, and actually learn the causal forces, the Newtonian way.
So it turns out, if you give a transformer too much memory, it becomes a historian, not a physicist. Let's get into the details.
Let's do it.
Okay, so to really get why this paper is so important, we need to talk about world models. We're not talking about an LLM writing a sonnet here.
No, not at all. The dream is to have a model that can simulate physical reality. Like it sees a ball falling and actually understands gravity, not just that the pixels are likely to move downward.
We wanted to understand the causal mechanisms.
Exactly. If a glass falls, the model should know it breaks because of momentum and, material science, not just because it saw a million videos of glasses breaking.
And this is where that Vafa et al. Paper is kind of the villain of the story, or at least the warning sign. They took a GPT-2 scale model and fed it 20 billion tokens of planetary orbits.
Which is just a staggering amount of data for what's, fundamentally pretty simple 2D mechanics. It's overkill.
And the results looked great on the surface. The loss curves are beautiful. It could predict the planet's next position with amazing accuracy.
Right. If you were just a leaderboard watcher, you'd say, done. AI gets physics now.
But they actually dug in. They probed the internal states of the network to see what it was thinking. And what did they find?
Well, they found that it had absolutely zero concept of gravitational force, didn't know F equals gm over r squared. It didn't get mass, didn't get acceleration, nothing.
Which just raises the immediate question, How on earth do you predict an orbit perfectly if you don't understand gravity?
You cheat. You memorize the geometry. The model is basically doing what Johannes Kepler did centuries ago.
Oh, interesting.
Kepler looked at all the observational data and said, hey, these things move in ellipses. He described the shape. He had no idea why. He just knew the geometric pattern.
So the transformer became a Keplerian model. It looked at the last 100 frames or so of the planet's path, recognized the curve, and just extrapolated the line.
Precisely. It's a historian. It sees a pattern from the past and assumes the future will follow that same pattern. But a physicist, a Newtonian model, doesn't need all that history.
Right. A physicist just needs the current state.
The current state and a universal law to figure out the very next moment. And that's the whole goal. The Stanford team wanted to figure out how to turn this AI historian into an AI scientist.
And they did it with these three inductive biases. Three constraints to stop the model from taking the easy way out.
The first one gets at a really fundamental problem, spatial smoothness.
This is all about tokenization.
It is. In that original Vafa study, they did what almost all LLMs do. They took continuous space, like an x-coordinate, and chopped it up into discrete bins. They had a vocabulary of about 7,000 tokens for position.
For text, that's fine.
Yeah.
Cat and dog don't need to be mathematically related, but for physics.
It's a disaster. In the model's embedding space, the vector for bin 100 and the vector for bin 101 are completely unrelated. They're orthogonal.
So the model has no built-in idea that they're right next to each other. It has to learn that from scratch.
Yes, by seeing just an unbelievable number of examples. It's like if you had a map, but every city was cut out and labeled with a random barcode, you'd have to watch traffic for years just to figure out that two cities are neighbors.
That's a great analogy. And they proved this was happening, right, with linear probing.
They did. They tried to see if they could find a simple map from the model's internal embeddings back to the real XY coordinates. And the R-squared score, which tells you how good that map is, was only about 0.86.
Which for physics is basically a fuzzy guess.
Oh, it's terrible. And when they visualized it, it was just so clear. A perfect circle in real space looked like 4 separate fuzzy clouds of points inside the model. The spatial map was just broken.
So the model literally can't see the world clearly because we fed it a chopped up version. I know the paper has a scaling law for this.
They do. They derived a formula that basically shows that to get a clean spatial map, your amount of training data has to grow way, way faster than your vocabulary size.
So with a vocab of 7,000, you'd need a truly astronomical amount of data to fix this.
Correct. Which leads to their first solution, inductive bias number 1. Restore the smoothness. You could shrink the vocab way down to like 128 and this is the better way, just abandon tokenization for this problem.
Go back to good old-fashioned regression. Just feed it the floating point number.
Exactly. Use continuous coordinates. The number 100.1 is inherently close to 100.2. You don't have to learn that. It's baked right into the math.
Okay, that seems so obvious. If regression fixes the map problem, why wasn't everyone just doing that from the start?
Because regression has its own very nasty skeleton in the closet.
Error accumulation.
Error accumulation, the drift. In a token-based model, you predict bin 100. Even if you were a bit unsure, you snap to that grid, it's self-correcting.
But with regression, you predict a float.
You predict 100.05 when the real answer was 100.00. You're off by a tiny amount. But then you use that slightly wrong number to predict the next step. So now your error is 0.003, then 0.01. It snowballs.
And then 50 frames later, the planet is either crashing into the sun or flying off to Alpha Centauri.
Precisely. In their early tests, the regression models just weren't stable. They'd crash the whole simulation.
So that brings us to the second bias, spatial stability. How do you stop the drift?
They used this really elegant trick called noisy context learning. During training, you deliberately inject a little bit of Gaussian noise into the input history.
You feed it imperfect data on purpose.
Do, but, and this is the key, the target you're asking it to predict remains perfectly clean.
Oh, okay.
So you're essentially telling the model, look, the history I'm giving you is a little bit shaky. Don't just blindly trust it. Learn to see the underlying pattern and correct back to the true path.
That's so clever. It forces the model to learn a kind of restoring force. It's like teaching someone to drive a car that always pulls slightly to one side.
Exactly. You force them to learn how to constantly steer back to the center. It builds in robustness. And they found with just a little bit of noise, the regression model stopped crashing. And once stable, they blew the token models out of the water on accuracy.
Okay, so we've fixed the map with spatial smoothness. We've stopped the car from crashing with spatial stability. At this point, the model must be learning physics.
Right. You would absolutely think so. But this is where the paper just pulls the rug out. Even with both of those fixes, it still wasn't learning physics.
Wow.
Nope. It was still a Keplerian curve fitter, just a much, much smoother and more stable one. It was still just memorizing the ellipse with higher precision.
And this leads to the third and honestly the most shocking bias, temporal locality. This part feels like it trolls the entire AI industry.
It really does. I mean, we are all obsessed with making context windows bigger. 1 million tokens, 10 million tokens. We want the model to remember everything.
And this paper comes along and says, actually, if you want discovery, you need amnesia.
That's the perfect way to put it. Think about Newton's second law, F equals ma. To calculate the acceleration, the force, you only need to know your current position and your velocity.
Which is a second-order differential equation.
Right. And to approximate that in a simulation, all you need is your current position at time phang and your immediately previous position at time t-1.
Just 2 frames. That's it.
That is it. 2 frames contain all the necessary causal information to compute the very next step. Any more than that is just historical context.
So they ran the big experiment. They trained one model with a long context length, like 100 frames.
So it could see pretty much the whole orbit.
And then they trained another model that could only see the last 2 frames.
And the results were just night and day. The model, with the 100-frame context, it learned a Keplerian world model.
It cheated.
It cheated. It saw the whole history and said, oh, I know this shape. It's an ellipse. Let me just figure out the geometry and draw the rest of the line. And the probes proved it. Its internal neurons were encoding geometric parameters like eccentricity perfectly. But the force parameters, barely at all.
It didn't care about force. It cared about the shape.
Right. But now think about the 2-frame model. It can't see the shape. If I just show you 2 dots on a page, You have no idea if they're part of a circle or a straight line or a crazy squiggle.
You have no global context. You're forced to look at the local change.
You are forced to abandon geometry entirely. The only possible way for that model to make an accurate prediction is to look at the change between those 2 points, infer the instantaneous force that must have caused that change, and use that force to calculate the next point.
By putting blinders on the AI, they forced it to derive gravity.
That's exactly what happened. And again, the linear probes confirmed it beautifully. The two-frame model showed almost perfect encoding of the force vectors and basically zero encoding of the global geometric stuff. It became a Newtonian world model.
That's such a huge insight. It basically says our mantra of context is all you need might be actively harmful for scientific discovery.
It really challenges that. Long context seems to encourage memorization and interpolation, but short context, if you match it to the actual dynamics of the system, forces the model to discover the compact causal rule.
You take away the crutch. If the model can't see the answer key in the history, it has to learn the equation.
Precisely.
I think we should talk about why this matters in the real world. They use that fantastic pink elephant analogy.
Yes, the pink elephant versus the gray elephant. It's the perfect way to explain out-of-distribution generalization.
So walk us through that.
Okay, so a gray elephant is just a standard orbit. It looks exactly like the stuff in the training data. The Keplerian model, the curve fitter, is fantastic at these. It sees the shape, says, I've seen this movie before, and predicts it perfectly.
It's in its comfort zone.
Totally. But now you introduce a pink elephant, maybe it's a really weird high-energy trajectory it's never seen, or an object's orbit gets perturbed by a third body. It's a shape that isn't in its memory banks.
The Keplerian model just breaks down.
It breaks. It has no template for this new shape, so it tries to fit its old patterns onto it and just fails miserably. The predictions go way off.
But the Newtonian model.
The Newtonian model doesn't care if the elephant is pink or gray or plaid. It doesn't rely on matching a global shape. It just looks at the last 2 steps and applies the law of gravity.
The laws of physics are universal. They apply to pink elephants just as well as gray ones.
And that's the holy grail of a world model. It separates the underlying invariant rule from the specific history. If we want to build AIs that can actually discover new science, we can't just throw bigger and bigger context windows at the problem.
We might need to be smarter about the architectural constraints, like locality, to force that discovery. It kind of changes how you think about scientific data. You don't just need to cover every possible outcome if your model can learn the rule that generates them.
That's the whole idea. Moving from interpolation, which is just filling in the gaps, to true extrapolation, stepping confidently into the unknown because you understand the principles.
So, to wrap this all up, the recipe for building an AI physicist, according to this paper, seems to be
1. Respect spatial smoothness. Don't arbitrarily tokenize the world. Use regression.
2. Stabilize that regression. Use noisy context learning to teach the model to be robust and self-correct.
And 3, the big one. Restrict your context. Enforce temporal locality. Don't let your model be a historian. Force it to be a physicist by giving it just enough information to solve the local problem.
It's just so fascinating because it runs completely counter to the main trend in the field. Everyone is racing to build bigger inputs, and this team is showing that in some cases, the answer is to make them smaller.
Sometimes the right constraints are what unlock real intelligence.
That's a great thought to end on. So if you're out there training world models, maybe take a second to ask if your giant context window is just giving your model an excuse to cheat.
Definitely worth checking.
And you should really check out the full paper for the scaling law graphs and the visualizations of the embedding space.
Yeah, the visuals of the broken versus fixed spatial maps are worth the read alone.
Thanks for tuning into AI Paper Podcast. We'll see you on the next one.
Bye now.